Okay, welcome to this review video on trigonometric concepts that you would have picked up during your grade 11 year in math, as well as those that were presented last semester in advanced functions. The first topic we should concern ourselves with is arc length. Now, if you take a look at the diagram provided, we see that there's a relationship between the length of the arc A, the angle that's opposite that arc, as well as the radius. And that relationship is that arc length is equal to the radius being multiplied by the angle theta. And it's very important that theta is in radians. Okay? You might be wondering what exactly is a radian. So if you think back to a time not all that long ago, is if the length of the arc is also the same as the length of the radius, then we can see from that that theta would be the ratio of A to R, which is in this case simply R divided by R, which would give us a value of 1. So that 1 is in fact 1 radian. And we do say that the radian is unitless because of that ratio. So for instance, if the length of the arc and that of the radius happen to be in centimeters, then you can see that those units would cancel when simplifying. Okay? So again, arc length is r theta, where theta is in radians, and radians is simply another means of measuring angles. Now, when you're using this formula, it's important to remember that if presented an angle in degrees, okay, you must convert it to radians. So let's say, for instance, in our example, okay, considering the diagram that we have, if the radius were, say, 2 centimeters, and theta were given in terms of degrees, and let's say, oh, for instance, let's go with 50 degrees. Okay, seems generous for that angle. Determine the length of the arc subtended by theta. So in our solution, we would note that A equals r theta. We have a radius of 2 centimeters. We also have a value of theta that we cannot use readily. Okay, and the reason being is that it's in degrees. So remember that 1 degree, okay, 1 degree has a particular relationship with respect to the circle. And that particular relationship is the following, okay? So for instance, we know that pi is equal to 180 degrees, or at least that is the equivalency. So if we were to determine 1 degree of measure, then we would have to take pi and divide it by 180 degrees. So in our case, what we will need to do in order to calculate the equivalent angle in radians for a 50 degree measure, then we would have to take the value in degrees and multiply it by a conversion factor, and that is pi divided by 180. Okay? So moving forward, as we complete our calculation, notice that the degree unit, okay, we're going to lose those. The only thing we'll be left with is a unit of measure in centimeters. So what we'll do is multiply 2 by 50, coming up with 100, and pi over 180. Now, no specificity is given as to how we want to express the answer. We'll leave it as an exact value in lowest terms. So we can take 20 out of the top as well as the bottom and end up with 5 pi over 9 centimeters. Okay. Next topic we should take a look at is that of the graphs of trigonometric functions. So this one is specifically that of the sine curve. Notice that x is in radians, so it is in a decimal equivalent. And if we were to graph this using a standard domain, okay, typically, I'm just going to extend this page for a moment. Typically, we graph functions. Let's just say f at x equals sine x. You'll often see this notation. Or you might see something like 0 to 2 pi. These typically tend to be standards. Note that these are equivalent to, okay, at least we'll write down the first one, minus 2 pi is about minus 6.28 radians. And then the upper bound would be 6.28 radians. Okay, the lower one, we might as well complete that one as well, so there's no confusion. So I'm going to go back up to my graphing space. I'm going to modify, I'm going to zoom in a little bit to account for that. And this should, that's a little bit, not quite enough. We'll leave it here. So you can see that one complete cycle of the sine curve begins here. That is if we 0 is our reference or the origin, and ends here at 6.28 radians approximately, okay, or 2 pi radians. So other things that we want to take note of with respect to this function is that the amplitude, okay, if you can take note of that, is denoted by parameter a. In this case, it's equal to 4. So that's what we can see here, is that the distance between the axis of the curve and that is the either a top of the curve and or the bottom is going to be 4 units, and that is the amplitude of the function. Base function, of course, we can modify that as an amplitude of 1. But for the sake of having a graph that's easier to read, example presents here as 4. Okay. Those are some basic features. You can also look at the graph and ascertain where its zeros are and how often they occur, the period of the function, the amplitude. Aside from that, you'll also know that there are other functions. There's the cosine function, which is simply a translation of the sine curve by 90 degrees. That'll come up in future work in the textbook for review. Another topic, if we kind of glaze over these quickly, is that of special triangles and exact values. So do recall that we had studied the 30-60 or the pi by 6, pi by 3 special triangles. Okay, so just for a reference, recall that pi by 6 is 30 degrees, and then this one here is 60. We had also taken a look at the 45 or the pi by 4 special triangle. The reason why these were so unique and special is that they provided for us specific values of coordinates on the circumference of the unit circle. Okay, and we had unwrapped the unit circle in order to create the graphs of the trig functions. Those specific values for the points along the perimeter and the circumference of the unit circle came from these triangles. So pi by 4 special triangle had side lengths of 1, 1, and root 2. And then the 30-60 triangle had side lengths hypotenuse 2. Opposite side to pi over 6 was 1, and then root 3. So some of the work that we had accomplished last year with respect to the special triangles and exact values was to evaluate trigonometric expressions. So for instance, in the following example, if I were to ask you to evaluate sine squared pi over 4 minus the sine of pi over 6, I would be counting on your ability to read those values from the unit circle and or from the special triangles. So the sine of pi over 4, let's determine this. So that would simply be, let's take this angle here. So we have the opposite side length. Here we have the hypotenuse. So sine of pi over 4 is 1 over root 2. We also saw that being equivalent to, if we rationalize the denominator, as root 2 over 2. On the other hand, the sine of pi over 6, that relates to the 30/60, or pi by 6, pi by 3 special triangle. Sine of pi over 6, here's the reference angle. This would be the opposite side length with a hypotenuse of 2. So we can see that the sine of pi over 6 is 1/2. So what we'll do is we're going to take these values and substitute them in here accordingly. Now the square indicates that this value will be squared. So 1 over root 2 squared minus the sine of pi over 6, which is 1/2. If you square 1 over root 2, you'll end up with 1/2. And thus the final answer, 0. Next topic, that requires review, were the compound, or that is the compound angle formulas. This is an excerpt from something you would have had or used last year with your Nelson textbook. So these formulas will allow for us to determine the sines of and cosines of compound angles. That is where we take two angles or more and add them together. So in terms of an example, why don't we use this relationship in order to evaluate the sine of, let's say, 5 pi over 12. Now notice that 5 pi over 12, that is with a denominator of 12, it doesn't really relate to special triangles all that well because of the denominators that we have given to us of 3, 6, and 4. So the idea is to try to split that angle so that we can say that it is a compound angle. So in terms of twelfths, 5 pi over 12, there must be a way that we can arrive at that. So for instance, we could take 3/12 of pi and add it to 2/12 of pi. What that does is it gives us a value of sine pi over 4 plus pi over 6. If you focus on what we have here in parentheses, you'll notice that this looks very much like the sine of a plus b. So what that means is we'll substitute our values of a and b and accordingly use the special triangles to solve, and we'll evaluate. So this would be the sine of pi over 4 multiplied by the cosine of pi over 6 plus the cosine of pi over 4 times the sine of pi over 6. Now using values previously found, this would be 1 over root 2 multiplied by, now cosine of pi over 6, we did not find that. We'll go back in a second and get that. Cosine pi over 4 is also 1 over root 2, and the sine of pi over 6 was 1/2. Going back to the special triangles for the cosine of pi over 6, what we can see is that we would take the adjacent side length and divide it by the length of the hypotenuse. Thus, this would be root 3 over 2. So moving forward and simply doing a little bit of fraction work, we would have root 3 over 2 root 2 plus 1 over 2 root 2. Adding our numerators together, we have this answer here. Another option would be to rationalize the denominator. So what we could do is multiply top and bottom. We could multiply bottom by root 2. Same with the top. This does not change the meaning, as this here, recall that this is equal to 1. So if we multiply the top by root 2, we'd have root 2 onto 1 plus root 3 all over 2 times 2. Finishing this off with 4. 2 2's are 4 in the denominator. Final topic necessary is that of trigonometric identities. Recall that we have the reciprocal identities. So 1 over sine, 1 over cos, 1 over tan, giving us cosecant, secant, and cotangent. We had established these identities at an earlier time, most likely in grade 11 course. This identity you learned and was proven in grade 11. These ones were provided last year, but can also be proven. We did look at double angle formulas, okay, and these were proven. Here's your double angles. So the sines and cosines, I believe, were proven on the basis of what we had learned here. So we had applied the subtraction and addition formulas to proving some of those double angle formulas. So in this particular example, notice that we have quadratic terms, we have a fraction, we have a tangent involved. So in terms of proving this, we need to split it out into left and right hand sides. And we often tend to work with the side that looks busiest. Okay, side that looks busiest. So we do need to come up with some form of identity, something that we can use to our advantage. Just by recognizing that there are some like terms in the denominator. Each term happens to have, I shouldn't say like terms, but have like parts, or like factors would be a better way to put it. We could factor out a cosine from the denominator, and that would leave us with a cos plus sine as a second factor. The reason why I'm putting that in there is if we can eliminate one of those factors from the denominator, then we could simplify this expression. In the top, notice that we have 2 squares. Okay, we have cos squared, sine squared. We also have a difference. Thus, we have a difference of squares. So we'd have cos theta minus sine theta multiplied by cos theta plus sine theta. The good news here is that once you have factored, and always only after you have factored, can we reduce the expression. That particular part reduces to 1 over 1. So we have canceled those terms. And from there, we can see that the left-hand side simplifies to cos theta minus sine theta, all divided by cos theta. On the left-hand side, or sorry, right-hand side, we have 1 minus tan theta. The strategy here is to convert your tangents to the quotient identity of sine over cos. If we acquire a common denominator, which will be cosine of theta, we end up being able to show that since the left side equals the right side, we know that that identity, cos squared theta minus sine squared theta, all of that over cos squared theta plus sine theta cos theta, it's getting quite lengthy, is equal to 1 minus tan theta for all values of theta belonging to R. Okay? The only thing that we would do in this case, that is, we understand that the expressions themselves are undefined. at certain values, but the left and the right hand sides are undefined for the same values. Thus, we can say that the identity is true for all values of r. Okay, so the work that you need to accomplish, that'll be in tomorrow's class. Let's take you to the course website right now in order that you can review some of these skills. Is in Unit 4, derivatives of sinusoidal functions, and the work to be announced. Here we go. Page 212.